All right, so you can see it's written somewhere there that this class is now live. All right, let's start by the definitions. We consider an experiment with n elementary outcomes. Denoted A1, A2, all the way to AN. So we have an experiment in which there are only capital N possible outcomes, denoted A1, A2, all the way up to AN. That's where we start. The first definition is for the sample space. The sample space is S equals the set that takes all possible elementary outcomes. That's what you call the sample space. So if I cast a die, for example, that has 6 sides, 1, 2, 3, up to 6, the sample space is the set of all possible 6 sides, 1, 2, 3, 4, 5, 6. Right? If I toss a coin and I know that the coin cannot just fall and stand still, then there are only 2 possible outcomes, head and tail, and that's my sample space. That's what we call the sample. If we have 21 students in this classroom, somebody is out there and I designed the experiment, get into that class, grab a student. And what's the sample space? The 21 students that are in the class. If I say get into this class and grab a girl, what's the sample space? Restricted to the girls. Only the girls that are in this class, because you will not get out of this class with a boy. If you say, grab a girl, and I'm interested only in that experiment, go grab a girl. It doesn't matter that there is somebody else. So you can have different experiments on the same set of people, and because the experiment changes, the sample space changes. It's not because the boys are sitting here that they automatically get into the sample space or get the person getting in here and grabbing a girl, because no boy is going to be taken, right? Does that make sense? And you will feel that more when we talk about conditional probability, which is when something has already happened, what is the probability of something else? Then you know that something already happened, then your sample space is restricted to what happened. And you don't care about the rest. That's why I like the definition in this way, with the example of getting into the class, grabbing a student, and then getting in the class and grabbing a girl. So you're restricting the sample space. Now, any subset, we know what a subset is, right? I'm assuming that anybody in this class has taken some kind of course where they define sets, subsets, included, belongs to, right? Like Math 305. All right. So any subset of S can be assigned a probability equal to the sum of probabilities of its element. Why? Because when we define the sample space as being the set of all possible elementary outcomes, again, elementary outcome means what? An outcome that cannot be divided into sub-outcomes, right? Like getting here and grab a goal, you can't get in here and grab half a goal, right? And say cast a die and look at the number that is on top. You can't cast a die and see 2 and 6 at the same time. You either see 2 or 6 or 1 or 3 or 4, and those are the elementary ones. But some events can be built on those elementary outcomes, like go cast a die and get 2 or 4. That's an event. It's not an elementary outcome. It's two different results, either 3, either 2 or 4, right? So it's very important to know that here we are talking about the elementary outcomes, not events, the outcomes that come straight from the experiment before you start doing anything with them, before you start defining events using them. So, and in that case, when you take a subset, because the elementary outcome cannot happen at the same time, the probability of any subset of that sample space is the sum of the probabilities of the elements that are in it. Does that make sense? Because those are mutually exclusive. That's the proper word for it. If you took 3 or 5, those events are mutually exclusive. They cannot happen at the same time. The elementary outcomes cannot happen at the same time. Now, if we denote P of AI, the probability of the elementary outcome. AI, then the following holds. These are the properties that show that a function that is defined set is the probability function. The first is that 0 is less than P of AI, and it's less than or equal to 1. So if somebody defines for you a probability on the set, on the sample space, and you figure that the value of that function for one of the outcomes is not between 0 and 1, then it's not a probability. So the probability of every single event must be between 0 and 1. That's the reason why most of the time people understand probability as chance. The chance to do it, the chance to do that. Because it's like 1 is like 100%. Right? 0 is 0. 0.1 is 10%. So some people always think of probability that way. So that's the easiest way to see it for the elementary ones. And the second, the probability of A1 plus probability of A2, if you add all the probabilities of the elementary outcomes, it must be equal to 1. So the sum of probabilities of the elementary outcomes is always equal to 1. And one of the most important rules is that if you have two events, C1 and C2, such that C1 and C2 are disjoint. This is what it means that C1 and C2 are disjoint, that the intersection of the two events is void. If the two events
are disjoint. So instead of writing this, you can say disjoint. Then the probability of C1 union C2 is equal to the probability of C1 plus probability of C2. And now you might be asking yourself, what does this mean and what does that one mean? And I'm providing the definition for that now. So the event C1 and C2, contrary to how you would be thinking logically, it means both C1 and C2 occurred in the experiment. So this is not like combining the two steps.
So if you want the event that is the intersection of two events, that would mean that you are looking for the outcomes that are in both events at the same time. The outcomes that are in C1 and are also in C2. So that's same as the intersection of sets. The event C1 and C2 means that both C1 and C2 occur in the experiment.
I can increase, zoom in, or you just have a shorter page. Okay. So anytime we write C1 and C2 intersection with C2, it means that the event C1 has occurred and the event C2 has occurred in the experiment at the same time. And that's why this here means that the two events are disjoint, because this means that there is no outcome, no elementary outcome that happens here and there. That's why it's empty. Nothing in common with the two. And again, be careful, disjoint doesn't mean independent when the time comes, because when the time comes, we start talking about independent, people get confused. They are disjoint, they are disjoint. Like say, what are the examples can I take? I want to detect something that is related to people. You have two couples living next to each other. They are disjoint, right? This couple is there in their house. This other couple is in the other house. That's two disjoint sets. Not independent often, because most of the time you want to know what your neighbors do, and that affects you. Does that make sense? Knowing what is going on in your neighbor's house affects you. So if we're interested in some quantity that is being measured with the relationship between the neighbors, that quantity is going to be affected by the fact that he is the particular one that is the neighbor. Right? Even though you don't live together, you are in your own house and there you are. Again, it's important to know that the two things are separate. Now, the other event, C1, I call this 4, union C2, means either C1 occurred or C2 occurred, or both.
So the or here is not exclusive.
Yeah, man, I can read now better. So I guess you guys are seeing better too on the board. Everybody agrees with that? Just that our board is smaller now, but we can read better. So thank God we figured that one out. So any questions before I change the board? Here we don't erase, we just change the board. See how good it is? We come out of the class with clean hands. Any questions? No? Okay. I see a couple of exercises again on the notions that I've introduced. One, show that the probability of the complement of a set is 1 minus the probability of the set itself. And then there's the probability of the empty set is 0. The answer is S, which is the sample space, is equal to C union C complement, right? When you take a set and its complement, that's what makes the sample space. That's the definition of the complementary set. If you put that set together with the original one, you get the entire sample space. Moreover, the intersection is empty. There is no point that is in the set and in its complement at the same time. It's not possible. But now, based on the rule number 3 that we had, the probability of S is therefore equal to the probability of C plus the probability of the complement. And that is because their intersection is empty. Whenever the intersection of two events is empty, the probability of their union is the sum of the probability, right? That's the rule I have here. When you have two events with intersection empty, the probability of the union is the sum of the probability. But this is the sample space. The probability of the sample space is always 1. That's because it's a sample space. And that is thus P of C plus P of the complement. And this leads to the probability of the complement of the set being 1 minus the probability of the set. That's it. So here we're just trying to use the rules, the properties that we just defined here. Any questions? Everybody happy? All right. Strange thing is I have two screens in front of me here. One of them is flipped. So I was thinking that maybe you guys are seeing a flipped screen until I realized that maybe you're seeing the other one that is not flipped. Which one are you seeing? Are you there flipping yourself to see it the right way, or it is not flipped?
It's not flipped.
All right, thank you. Any questions? Now, no? All right, so now if this is correct, then S is S union the empty set, right? And S intersection with the empty set is empty. Agree? By that same rule that we just used here, the probability of S equals probability of S plus probability of the empty set. So that's still using this property. Right? Because the two sets are disjoint, the intersection is empty. And so the probability of S cancels, and you have that the probability of the empty set is always equal to 0. So when we are giving the rules of probability, we don't really have to say that the probability of the empty set is 0, because once we know that the probability of the sample space is 1, the probability of the empty set will follow from there is 0. Questions? Is this making sense? I don't want to lose anybody. Because I used to lose everybody. Trying to make sure that we're on the same page. Is that true, Rachel?
Not at all.
Are you sure? I know you took some courses with me
I did.
when I was still a good guy. All right. Anyways, so next example, I'll try to let you guys think. Exercise 2. Show that when the C1 is included in C2, we have that probability of C1 is less than or equal to the probability of C2. Which means that a smaller event always has a smaller probability. It makes sense, right? But how do we prove it? That's the thing. All right, I'll give you 2 minutes or 1 if you are quick. And the hint is that it will use that same property that we just used in the first 2. Please, when you find the answer, let me know. With these masks, I tend not to recognize some people. That I really, right? Yeah, because that I couldn't think of. I was afraid, right? You have it already, James? Maybe Laurel? Not yet? Okay.
Are you talking about me?
Yeah.
I was thinking we could use definition B,
B. Let me see.
any subset of S can, oh wait. It,
Yeah,
so
Michael?
any subset of S is equal to the sum of the probabilities of its elements. So if C sub 1 is an element of C sub 2, then we could use B.
You are correct, but then that will only work if we are talking about discrete. So you're not wrong. But the rule that we have here is in general for any probability measure, any experiment, and that will include, as later you will see, the case where you have continuously many things you can't count them. Okay, but your proof does work for the examples that I have been using here. The hint that I was given is that we should use the same property that we used to prove the first two things here. The fact that you have two sets with intersection empty. So here what we need to do is use C1 and C2 to create two sets that are disjoint that will help you show that one is smaller than the other one. Correct. So that's the thing. So you take out of C2 all the elements of C1, then you will get a set that has nothing to do with C1. Does that make sense? And the notation for that, as she said, is C2 minus C1, that you do that in 305. But here, we use the language that we have here, the intersectional events as of now, right? So what is C2 minus C1 in terms of intersection? How do I write C2 minus C1 using the intersection? C2 intersection with C1 complement. So if I take in C2 the elements, look by definition, you will see that it works. Take in C2 the elements that are not in C1. What is that? It's C2 intersection with not C1, which is the complement, right? So here we can create, to answer this question, say C1 and C2 intersection with C1 complement. Have this joint, which means that their intersection is empty, right? And C2
Can you move the page up, please?
oh, sorry. I don't see the board. So how do we continue if we have this? They are mutually exclusive. That means that's what we said. The two are disjoint already. How do we use this fact to prove that the probability of C1 is less than the probability of C2? What's that again? Yes. So, and what is the union of the two sets? probability of C1 union, I'm just writing down what you just told me, okay? C2 intersection with C1 complement. What is it equal to? It's probability of C1 plus probability of C2 intersection with C1 complement. Okay. And what is C1 union C2 intersection with C1 complement?
Hmm? You know that there must be elements of C1 in it, right? Huh?
Not S, but C1 union C2. Is that true? Uh-huh. If you say it's C2, again, let's check. This is not correct, okay? I'm asking the question. If it's true. If you say it's C2, okay, you do know that in this set are elements of C1, but all elements of C1 are in C2, right? So you have elements of C2 that are not in C2 and the elements of C2 that are not in C1. What does it form together? Yeah. Mhm. You want to turn to this? Oh, no, it shouldn't be. It's what it was. It's inside C2, so it's still C2. So it is okay afterward. Why? Because the C1, all elements of C1 are in C2. And if we take the elements of C1 and we add the elements of C2 that are not in C1, what do we get? We get C2, right? That's the thing. And so, which is P of C2, because C1 is in C2, and that is P of C1 plus P of C2 and C1 complement. But this thing, by definition, is positive. So, the probability of C2 is larger than the probability of C1.
Then be very careful with those things. Not to rush and you don't do.
Why is this correct? Because C1 is in C2. Right here. Is everybody okay? Unfortunately, you can't see me, but I want to hear your voice. Are we fine with this? Anyone needs something to be explained? Nope. Now the last exercise here, this one, please do it completely for me. In general, probability of C1 union C2 is equal to P of C1 plus P of C2 minus P of C1 intersection with C2. Then it's the same rule that we will use here. We practice on that 1 minute. Please, when we have an exercise in class, complete the work with us. It is important because those exercises are what I'm going to shoot back at you when the time comes for a test. I'm not going to create problems from somewhere else. I'm going to take them from your lectures and your homework.
Hey, Dr. Longla, you became really quiet. We didn't catch that last part.
I was saying that please, when we are doing the problems in class, make sure you follow and do too, because I will shoot them back at you when the time comes from the test. Your test will have problems from the classwork and from your homework. So it's good to do when we ask to do so, even if it's difficult. We learn with it. Nobody gets killed for getting a wrong answer. We have one more topic to cover, so let's finish this one quickly. Anyone to try? I can also take the answers from you by showing your work. As you have a camera, you could just show it and everybody will see it. So what's that? You have the answer already? We use the same principle as in the previous one. Yeah. And what does that mean for the text? The same text that we just used. How do we get the elements that are in C1 union C2? Those are elements that are in C1 and the elements that are in C2 and not in C1. Is that correct? Do we agree? That's the formula we use. We just use on top there. Do we agree with this? So if that's the case, and we do know that the intersection of these two sets is empty. Why is it empty? Because no element of C1 is here, right? So we can apply the rule that the probability of the union of the two sets is the sum. So we have one piece. Two are missing. We are still missing P of C2 and the intersection. So how do we handle this piece to obtain the last part? So the hint here could be, that has to do, if you look at this piece, has to do with taking something out of C2, right? So we will consider C2. Am I making sense? This piece here is what we need to show that is equal to this. So we need to relate this to that piece. That's the spirit of the proof. And now when you look at these two sets here, you can see that the two sets are disjoint, right? That the elements of this set are not here, because here we have the elements of C1 complement, and here we have the elements of C1. Does that make sense? That rings a bell. So here we have the elements of C2 that are in C1, and here we have the elements of C2 that are not in C1. Oh, if we combine the two of them, what we get? We get C2, correct? So all we need to do is create this set from C2. And we say, but C2 is nothing but C2 intersection with C1 complement union C2 intersection with C1. If I take all the elements of C2 that are not in C1 and I take the elements of C2 that are in C1, then I have all the elements of C2. And as said earlier, these two sets are disjoint. Their intersection is empty. And that's the reason why the probability of C2 is equal to the probability of the first C2 intersection C1 complement plus probability of C1 intersection with C2. And so we can solve for this. We solve for this, which is P of C2 minus P of C1 and C2, which is exactly that. Does that make sense? So we solve for this, and we replace in here. We replace in this formula. And that's P of C1 plus P of C2 minus P of C1 and C2. Let me do that here. Running out of space, but I can do right. P of C1 and C2. C1 complement of C2 is P of C2 minus P of C1 and C2. And we take that back into this formula here. And we get P of C1 minus C2 equals P of C1, that's the first part, plus P of C2 and C1 complement, which is what we just got, is P of C2 minus P of C1 and C2. That's it. That's how you prove that formula. We use it every day, but we need to know how to prove it, right? From the principle. It makes sense when you look at it that, yeah, when you're adding things, you need to subtract the intersection, but how do you use the properties to prove it? Because this course is mathematical statistics, so we do the mathematics that is behind the statistics. That's what it is. So you need to formally prove everything to make sure you understand why it is being done and why it is correct, not because intuitively you think it's okay. As you will see later in some classes, your intuition is not always the right thing. Is there any question? Are we good with this proof? All right. So if we have the silence, it means everything is fine. So we move to the next one. All right. Here we're going to deal with something called calculator, which is counting. The things that we will need to use in the next lectures. I'm just defining them today. So we're going to define the permutations, the combinations, how to draw with replacement, without replacement. Those are the things that we want to talk about now. But before that, actually, it would be okay to say for a sample space with equally or with equiprobable elements, which means elements have the same probability. Equiprobable, which means that the elements have the same probability. The probability of an event A is equal to NA over N, where NA is the number of outcomes in A, which is the number of elements of A. Right, and capital N from the beginning is the total number of elements that you have in a sample space. Very important to have that separately as well. It's just 1 over N. Right? So all elements have the same probability. That's why you just count the number of elements and then you divide by the total number of elements. And the reason why I give this as an example at the end is that in general, when you start by that, some people get confused. They think that every time we say probability, you count the elements and divide by the total number. It's only when the elements have the same probability that it works. They don't have to have the same probability. Like say, I give you a die that has 2 sides with number 6, and all other sides are 1, 2, 3, 4, and there is no 5. You have 2 6. 6 has probability 1/3, and all others have probability 1/6. It's not, they don't have the same probability. So you can't just now say, hey, I'm going to just count how many times I got 6 and then divide how many times I got 3 and divide, because you'll be wrong. Now, in this setup, when we need to count the number of elements, that's when we go with the counting principle. How many elements will be in the set? How do you count that? If it's just 5, 6, 7, it's okay for you to just say 1, 2, 3, you count. But if you have a large number, how do you do? How do you know how many numbers are going to be in that event? Depending on the wording of the event, you should know how to find the number of elements that is in it. That's where this part comes. Okay? So first, drawing without replacement. And the order. Now, so when the order of the elements is important and you are drawing without replacement, how do you find the number of elements that will satisfy a given thing? So we always say, for example, select K order elements from N.
Let's say, for example, I ask someone to come 5 times into this class and pick a student to get out. You have your names, you are different, every single student is different. The order in which he's going to come out to the student is important. Does that make sense? In how many ways can he get into this class 3 times and come out with 3? Or in how many ways can he get into this class and come out with different sets of students?
So and we call that the number of permutations. Of A elements selected from N elements. And the notation officially is PKM, which is N factorial divided by N minus K factorial.
We know what n factorial is, right?
So N factorial is N times N minus 1 and N minus 2 all the way down to 2 times 1, the product of all integers up to N. So if I say get in this class where we have 21 students and select 3 students without replacement and the order matters, selecting 3 out of 21 would be 21 factorial divided by 21 minus 3 factorial, which is 21 factorial over 18 factorial. And the properties of factorials are that you can get this down. Factorial n is n times factorial n minus 1. So you can always get it down by 1 to put the factorial on the next one. So here, this is 21 times 20 times 19 times factorial 18 over factorial 18 and the cancel. Does that make sense to everybody? All right. I'm not interested in knowing how much it is everyone, so we can keep it like that. Then we have the I mean, here drawing is not like drawing a line. Sometimes English is crazy. Not my language, but sometimes I say things and I think, how come these words people are using and they don't realize? They're saying something new. You say, draw without replacement, I take it fast. I write without replacement. So I draw without replacement. It's not really good. Especially when you're teaching calculus with the integral and partial fraction. A lot of crazy things going on. U substitution, du over u. It's a mess there. Anyways, let us focus on this one. We have our own mess here. So drawing without replacement where order doesn't matter. And actually, when you're drawing without replacement and the order doesn't matter, it's the same thing as taking everything at the same time. Does that make sense? Because it doesn't matter in what order you got them. It's same as saying, okay, get in here and take 3 students. If you don't care which one is the first, which one is the second, which one is the third, right? Or I say get into this room and get 3 chairs. Who cares which one is the first? 3 chairs, right? So why not just get in and get the 3 chairs instead of going in, take 1 chair, get out, and come take another one, don't take a third. It's the same thing like grabbing the 3 chairs at the same time. The order doesn't matter. So when the order doesn't matter, what we need to do is to remove the orders from the number of orders that we had. Remember in this problem, we had orders, right? So we select the key things and we order them. Now here, if we don't have to order, then we get to remove the order. How do we get the orders of k elements? Factorial. So if I want to get this answer, it's going to be divide this answer by k factorial. Because that would be removing the orders. Out of the k orders, take only 1. Is it clear? Because when the order matters, every set of k elements is represented factorial k times. Because of the whole different orders, right? And out of each of them, you need only 1. So you need to divide by factorial k. And it's the same factorial k for every single set. Does it make sense? All right. So here, we call this also the number of subsets of k elements for a set of n elements. This is the second example that I was giving you, that you can decide to take everything at the same time. If you take everything at the same time, then it's a subset that you're taking, right? And so we call this, the notation is choose k out of n, which I just said is the permutations divided by k factorial. And so that is n factorial over k factorial times n minus k factorial. Called number of combinations of k out of
if I have 4 elements, how many subsets of 3 can I get? That's, for example, the question. How many subsets of 3 elements can I get from a set of 4 elements? Is everybody okay already? So example. Choose 3 out of 4. That's the number of subsets of 3 elements of the set of 4 elements. And the formula says choose 3 out of 4 is 4 factorial over 3 factorial times 4 minus 3 factorial, which is 4 factorial over 3 factorial, that's 4. So there are exactly 4 subsets of 3 elements of any set of 4 elements. And for this example, you can list them. Let's say our set is A, B, C, D with 4 elements. What are the subsets of 3 elements? And you can list them. A, B, C, A, C, D, A, B, D, and B, C, D. Is there anyone left? That's all of them. There's nothing left. The formula says there is nothing left. I already wrote 4 different. There is nothing else. So I'm not going to look for others because I know there are others. When you're answering questions on probabilities, it's good to know these things that can tell you ahead of time whether you're on the right path or not. There was one last thing. Do people want to go already? At what time do we end? Let's say, just say 2 minutes ago. All right, let me finish the last thing, okay? It's not that much. Just one little thing at the end. Drawing with replacement. In this case, usually the order doesn't matter. So we say pick K elements with replacement out of n. And the answer is n raised to the power k. Why is that? Because when you want to pick the first element, there are n. You want to pick the second, there are n because you replace, you put it back there. You want to put the third, there are still n. And you multiply them k times, so you have n to the power k. All right? Good. That's it for today, I think. Thank you very much for your time. I will post all necessary material on Blackboard, and we shall see you on Wednesday. Thank you.
Thank you, Dr. Longlow.
Thank you. See ya.
Dr. Longlow.
Yep. What? When you get the homework, you need to be able to have your textbook, right? So, and it's every week you get your homework assignment. So, and if you don't get it before then, it's better that somehow you get a copy of the pages that are necessary. You can come to my office, you can make some copies till the time you get your book. Huh? You haven't there? You haven't yet? Because
Because we have one textbook here. I'm not sure that it's available online, but you can try to search it. Some courses have free available online, but I'm not sure. I don't know if this one has. Yes. Yes, I will post it for all the videos.
Oh, so, and then I didn't stop this thing, it's still recording. All right, let me stop it first.